so today we're going to go ahead and begin unit number 8, which is entitled Write and Graph Exponential Equations. We tried to expose you to this a little bit yesterday when we did our opening problem, which was finding the population of Bemidji, Minnesota, given that its population grew 5% every year. And really the goal of that was, number one, to expose you to different types of problems, not just being linear ideas, which is what we've been focusing on for most of second semester, but also was to kind of give you a hands-on idea of what type of topics we're going to be taking a look at as we move on, because we are leaving the world of the linear behind and we are moving now into this idea of exponential equations, exponential functions. That's what Unit 8, Unit 9, Unit 10, and Unit 11 are actually going to be mostly about. So just to give you a quick idea, there are going to be two standards that we're going to talk about in Unit number 8. Standard number 30 is talking about graphing exponential growth and decay equations. Now again, they go in and they describe all 4 levels of this. We don't necessarily know at this point in time what a growth function is, what a decay function is. Those will be things that we talk about as we define those in each of our 2 sections in Unit number 8. And then our second standard is going to be write exponential growth and decay equations. And really what I'm going to tell you is we're going to kind of do all of this together as one big idea, okay? So we're going to take a couple days and we're going to look at exponential growth functions. We're going to take a couple days and look at exponential decay functions. And when we do that, we're going to be both graphing and writing those functions as we go. So next week, you will be taking an assessment that will have both of those standards tied in together. So you'll be taking standard number 30 and standard number 31 checks at the same time. We'll review a little bit, and then you'll be taking your summative assessment after that. So, getting into unit number 8, though, we're going to begin today is the first of our 2 days talking about exponential growth functions. And so we need to get through a couple of definitions first, and then we'll get into the examples that we're going to take a look at as those come up as well. Okay? So our very first idea is, and this kind of goes for exponential growth and exponential decay, all right? We need to talk about what is an exponential function. So an exponential function is defined as a function in the form y equals a times b to the x power, where a is not equal to 0, b is greater than 0, and b is also not equal to 1. Those are 3 things that have to be true in order for a function to actually be an exponential function. Okay? I'm going to pause here for just a couple of seconds, give you an opportunity to get that down into your definition, and then we'll talk a little bit more about it. Alright, so pretty much every function that we write, that we graph, is going to be in this form of y equals a times b to the x power. And again, I'm trying to relate this to something that we've done previously, so I would like to bring back into this idea. When we talked about writing an equation in slope-intercept form, we always said that it needed to be in the form y equals m times x plus b, where we had values that we were always going to be plugging in for m. Of course, m represented our slope. And we also had values that we were always plugging in for b, which represented our y-intercept. Okay? But this value of y and this value of x stayed as an x and a y throughout the entire equation. Okay? Now again, we knew what m was, we knew what b was. It kind of helped us give a shortcut to these ideas. Okay? What I want to talk about is over here, y equals a times b to the x power. Okay? Some similarities. This y, just like over here, is always going to be a y. Okay, we're not going to have numbers to plug in for that or anything else along those lines. It's going to stay as a y value. And this x is always going to stay as an x, just like this x did over here. Okay? There's a couple differences, though, or one difference that's significant. Over here, your x was being multiplied by something, which made it be a linear function. Whereas over here, your x is actually going to be an exponent. That's what is going to turn this into an exponential function. Okay? We will have values to plug in for a, we will have values to plug in for b, but we're actually going to save that for Friday, and we'll specifically start talking about what does this a value represent, what does this b value represent as we go forward. Okay? But at least kind of giving some parallels between functions we've seen before and this idea of y equals a times b to the x power. Now, we're specifically in section 7.4. We're going to write and graph and equations for these, but we're going to focus specifically on what an exponential growth function is. Okay? So what makes an exponential function an exponential growth function? Okay? And that's all dependent on what the b value is in this particular problem. Okay? So an exponential growth function is defined as an exponential function, which again, it must be in the form y equals a times b to the x power. But now we're putting an extra stipulation on b. Before we said that b has to be greater than 0, okay, and b cannot be equal to 1, which would imply in this setting that b could be a number between 0 and 1, or a number bigger than 1. Okay? With an exponential growth idea, though, we're strictly saying that the b values must be bigger than 1. Okay? And if you think about the example that we did yesterday, a population of a town that had a 5% growth, okay? When we got done and wrapped up that problem, our b value, okay? We didn't call it a b value yesterday, but we can call it a b value now. Our b value was 1.05. It was a number larger than 1, and it showed an example of something increasing in size over time. And in that particular problem, the population of the town was what was increasing. Okay? So as long as your b value is anything bigger than 1, and again, we don't necessarily think whole numbers all the time. 1.05, 1.1, 1.3, those are all b values that are bigger than 1. Those will all be examples, when we get done graphing, of an exponential growth function. Alright? So these are the two ideas that we're going to talk about today. There's a third one, talks about compound interest. This is more of an application type problem, and as I talked about the other day, we're going to save our applications on Friday, and we're going to specifically today kind of talk about the nuts and bolts of what is an exponential function. Okay? Alright, so example number 1. In example number 1, they're asking us to write a rule for this function. And again, I'm going to try and do a lot of compare and contrast ideas between what we've done previously with linear functions and what we're doing now with exponential functions. Okay? So here's our first compare idea. Alright? So I'm going to real quickly here give you a different table. Okay? This is a problem that I would have given you back in unit number 5, unit number 6, unit number 7, where we were starting to talk about writing equations from tables. Okay? And so when we started writing the equation from a table, here's what we did. We checked to make sure that we had a consistent change in our x's. Okay? And what I mean by that is we were adding the same thing to each quantity in here to go from one x value to the next x value. Okay? And you can see that from these basic 5 values, to go from -2 to -1, from -1 to 0, from 0 to 1, and from 1 to 2, we are constantly adding a 1. Okay? I don't necessarily always have to be adding 1s, but the numbers that I'm looking for needed to be the same for this pattern to continue. So whether I was adding 2s, or 3s, or 4s, we were looking for a consistent difference in your x's. Okay? And then what we were able to find out is we also, because it was linear, had a consistent difference in our y's as well. It wasn't always adding. Okay, in this case I picked numbers that were subtracting, but you were going from positive 12 to a positive 10, which meant that you needed to subtract 2. And if you went from a positive 10 to a positive 8, you again subtracted 2, from 8 to 6, and from 6 to 4, you were also subtracting 2. And what we found out was when these were consistent differences, this represented something in your equation. Okay? And that was the case because it was linear. You were adding or subtracting numbers on your y tables to get the next y values. Okay? That's not going to happen anymore. So you'll notice that when we look at example number 1 here, as you go along your x values, you're still looking for the same consistent difference here. Okay? So from -2 to -1, I'm adding 1. From -1 to 0, I'm also adding 1. From 0 to 1, I add 1. And from 1 to 2, I also add 1. Okay, so we still have our same consistent differences in our x's. But you're going to notice that we do not have consistent sum or differences in our y's. Okay? And I'll ignore the fraction here for a minute. But if I'm going to go from 2 to 10, that means that I need to add 8. But when I go from 10 to 50, I'm adding 40. And when I go from 50 to 250, I'm adding 200. So I'm not adding or subtracting the same numbers in this idea, which simply tells me this. This table does not represent a linear function. That doesn't mean we can't write it, it just means that it's not linear. Okay? So, if it's not a linear function, the next idea that it could be is it could be an exponential growth or later on an exponential decay function. Okay? Well, how do we determine if it's that? Well, instead of adding the same thing to each number, okay, again, I want you to think back to the population problem. We didn't add a consistent number in each one of those to go from year 2 to year 3 and from year 3 to year 4. What we did was we multiplied by a consistent number. And that's what you're looking for here. Okay? And again, if you're not very good with fractions, then don't start with the fraction portion of this. Start with two whole numbers. Okay? So we begin by saying, what do I multiply 2 by to get to 10? And that answer is I have to multiply that by 5. Okay? Well, what do I have to multiply 10 by to get 50? Well, if I multiply 10 by 5, I'm also going to get 50. And what do I have to multiply 50 by to get 250? Well, again, if I multiply that by 5, that's what's going to give me 250. So notice that I have a consistent multiplication happening in this problem as we go through it. Now, how do I check from here to here? Well, if I take 2/5 and multiply that by 5, the question is do I get 2? And the answer, of course, is yes. So, this is a consistent product in all of these problems. Okay? Now, where does this fit into my equation y equals a times b to the x power? Okay? When you find what you are consistently multiplying by, which in this case we said was 5, this value right here represents your b value. Okay? Now, we still don't know what our a value is yet, but we definitely know what our b value is. So when I take my function, y equals a times b to the x power, you again have just found a value that you can plug in for b. So we now know that y equals a times 5 to the x power. Now you're not done because you still don't know what your a value is. So the question becomes, how do I find it? Well, think about this. When we knew y equals mx plus b, okay, and you knew your slope, what you had to do is you had to take a value that was in your table, plug it in, and figure out what the y-intercept was. Okay? Now, I'm not saying this is my y-intercept. I'm not saying it's not either, but I'm just not saying that it is. But we're really able to do the same thing. You have 5 ordered pairs in a table here, okay, that you can choose to use for your x and your y values. And if you choose to use those for your x and your y values, then you should be able to solve that equation then for what a is. So what I would suggest is picking one of these values that you like, and it doesn't matter which one, okay? But we're going to pick it, plug it in, and see how it works. And I'm actually going to do this twice, just so you guys can see that it doesn't matter what values we pick. So let's say that I want to choose this one right here, 1 comma 50. All right? That would mean that in place of y, we're going to plug 50 equals a times, we know that this value is 5, okay? And then our x value is equal to 1. So, if we evaluate this function, okay, we'd have 50 is equal to a times 5 to the first power is just 5. So if I want to solve that equation for a, I can go ahead and just divide each side by 5. And when I do that, it's going to show me that a is equal to 10. Now you might say, well, that's really cool. Is that going to work every time? Absolutely. Okay? So, here's another one. And I'll be honest, this is probably my favorite one to pick right here. Okay? Pick 0 for x, pick 10 for y. So, plug 10 in for y. And this is equal to, again, let's say we don't know what a is. Okay? But we know that x value is 0. So we'd have 10 is equal to a times, well, we just got done talking about an entire unit of exponent properties. 5 to the 0th power, remember, is always equal to 1. And 1 times a, of course, is equal to a. So no matter what point you use out of your table, you're going to get an a value that's equal to 10. Okay? So then, when I come back over here, we already found our b value. That was the constant multiplication happening in the problem. And then we plugged that back in and we found out what our a value was. So our final equation for this becomes y equals 10 times 5 to the x power. And if you were to take each of these x values and plug them in, following the order of operations, you're going to get each of these y values out as an output. Alright, our second example that we need to take a look at today is they're going to ask us to graph this function. Okay, and they're going to give us different functions as we go through. Then they're also going to ask us to identify the domain and the range. Now, if you recall from earlier this year, when we talked about identifying domain and range, the domain, remember, told us what are the values that we're able to choose for x, and our range says what are the values that we are getting out for our y's. Okay? Same idea as before. So, there is no, I'm going to be very upfront with you, there is no shortcut way to graph an exponential function. Okay? It's not like, well, I'm going to teach this for 4 days and then come back and say, hey, look at this. Just like y equals mx plus b, I can give you a super shortcut. That's not going to happen. Okay? Now, there are some shortcuts that we're going to discover right away, but when it comes to creating a table to graph an exponential function, you're going to have to create a table the entire time. Okay? Alright. So, let's go ahead and create our 5 values, and then we'll plot our graph, or plot our points, and then draw our line. Okay? So, we're going to show a little work on these as we get going, because some of these are not going to be very nice looking problems. Because, here's what I'm going to tell you. I want no decimals in my table. And if you type these into your calculator, you're going to start getting some decimals. Okay? So, let's begin with our first x value. Plug in -2. We have y equals 5 times 3 to the -2nd power. Now, again, the reason that we just did unit number 7, which was all of our exponent properties, is so we know how to deal with negative exponents. And we said that we know that we can deal with negative exponents by taking any negative exponent and flipping it. If it's on the top of the fraction, move it to the bottom. If it's on the bottom of the fraction, you move it to the top. In this case, it's on the top of the fraction, so let's move it to the bottom. So this now would become y equals 5 over 3 to the +2 power. And now I'm going to actually be able to evaluate that on my calculator. So the 5 on the top is going to stay as a 5, and my 3 squared is going to become a 9. So when we plug in -2, this is going to turn out to give me a +5/9. Okay? Yes, I understand that is not going to be the nicest number to graph, but we will deal with that. Okay? And now we're going to repeat this process for the other ones. So what about y equals 5 times 3 to the -1st power? Well, again, we don't want to use a negative exponent. We know that we can make that negative exponent into a positive exponent when we move the 3 to the bottom. And then, of course, 3 to the 1st power is just equal to 3. So the output of this problem turns out to be 5/3. There's the next value that goes into my table. Okay? Plug it in our next one. Plug in 0. Y equals 5 times 3 to the 0th power. Again, we already know what the 0th power is. 3 to the 0th power should just be equal to 1. And when I multiply 5 by 1, we're going to get an output of 5. Okay, then we'll plug this in with a 1 and a 2 as well. Okay, so now we have y equals 5 times 3 to the first power. Okay, no negative exponents in this one, so this becomes y equals 5 times 3 to the first is just 3. And now we have y is equal to 15. And yes, this is off of my graph. We're going to find out that exponential functions very quickly get off of the graph. Okay? And then our last one, y is equal to 5 times 3 to the second power. We're going to evaluate using order of operations, so we're going to square first. So y equals 5 times 3 squared, which is 9. And now we have y is equal to 45. This is the last value that's in my table. Now, how do we graph these? Okay, that's what we need to talk about, then identify our domain and range. Okay, first of all, again, you're not going to have a whole lot of points that are in your table that you're able to graph. Okay, it doesn't often work out that way because, again, exponential functions, they increase very, very rapidly, much faster than what a linear function did. Okay, so let's start with the easiest one. Start with your y-intercept in this problem, which is 0, 5. That's the easiest point. That is the only integer point that shows up on my 10 by 10 graph paper here. Okay? Now, 1, 15 is already going to be all the way up into here. So I'm not really going to be able to sketch that in here, but I'm going to have to show, like, from this point, it goes up really, really fast. And 2, 45 is all the way up into here. Like, that's growing super, super fast. So that graph is really going to have to climb as we start to draw. Okay? But what about these? -1 and 5/3. When we think about what 5/3 is as a fraction, it's bigger than 1, but it's smaller than 2. In fact, it's 1 and 2/3. So if I graph that, go back 1, and go up 1 and 2/3, I'm going to kind of just have to eyeball that. Somewhere between 1 and 2. Closer to 2 than it is to 1, but somewhere in between those two. Okay? And then this one here, -2 and 5/9. Well, 5/9 is really small. Okay? So 5/9 is a number that's bigger than a half, but not a whole lot bigger than a half. So what we're going to do is graph that point, -2, comma, and then a number that's really close to 1/2. Okay? Now, what do we do from here? Well, before we do this, and we're not going to do these all of the time, okay? But what happens is my x values get smaller and smaller and smaller. Okay? What happens when I plug -3 in, when I plug -4 in, when I plug in -5, -6, and so on? Okay? Well, again, we're not going to do this all the time, but I want to show you here real quickly, so when we do this at the front, then it kind of takes care of everything from there. So what if I plugged in -3? Y equals 5 times 3 to the -3rd power. Again, we wouldn't want to evaluate this with a negative exponent, so we would end up taking that negative exponent and moving it to the bottom, and it would become 1 over 5 to the 3rd power. 3 to the 3rd power. And if we took 3 to the 3rd power, we'd get 5/27ths. Okay? Well, what do we know about 5/27ths? Well, it's a number that's smaller than 5/9, but it's a number that's still positive. Okay? So, that would be somewhere like right in here. Then, what if I took 5 times 3 to the -4th power? Again, to deal with that negative exponent, we would move that part to the bottom, and then we would evaluate. And this would become 5 over 81, which is a number that's smaller than 5 over 27, but it's still a number that's bigger than 0, so now we're going to be right into here. So as my x values get smaller and smaller and smaller, okay, what's actually happening is my denominator is getting bigger and bigger and bigger and bigger and bigger. why my numerator stays as a 5. So if my numerator stays as a 5 and my denominator continues to get larger and larger and larger, it means that my fraction is getting really, really close to 0. But I emphasize, it's really close to 0. It's never going to be 0. So as I go to create my curve here, I don't ever want to cross this x-axis here, because crossing the x-axis is going to show that my x values are actually getting to be negative, and they're not going to be negative. Even with negative exponents, those are not going to be negative. So, this is how we're going to create our graph. We're going to create a smooth curve here that ultimately gets almost to 0, but then just continues forever and ever and ever in that direction and really doesn't change height. And as we go to the other side, it's going to grow, as we talked about, extremely fast in this particular idea. This is the graph of y equals 5 times 3 to the x power. Now, we did say we need to identify our domain and range. Okay? So what do we know about our domain? Again, our domain would say what are the values that we are plugging in for x. Okay? And again, we're going to get some really small numbers here, but we could keep plugging in values for x from -3, -4, -5, -6, -7, all the way down to -infinity. And we could keep plugging values in for x from 3, 4, 5, all the way up to positive infinity. So what we find out is that in this particular function, there are no restrictions on your domain. And if there are no restrictions on your domain, then that means that your domain is all real numbers. Alright, what about your range? Well, your range did have a restriction, and that's something that we just got done talking about. Okay? Your range in this particular idea, we said, was never going to get to 0. It's going to get really, really close, but it's never going to get there. But it is going to grow really fast. And it's not actually going to have a top on it because this has an arrow on it that shows that it goes on forever. So we have a lower bound, but we don't have an upper bound for our range. So as a result, we're going to say that our range, y, is greater than. Not greater than or equal to, because it's never going to be equal to, but y will always be greater than 0. Again, we don't want to include the equal sign, because as we've shown, it's never going to be equal to 0, but y will always be positive. Alright. Okay, let's go ahead and flip it over. We've got one more to take a look at here. We're going to talk about example number 3. We've got 3 different functions. Y equals 4 to the x, y equals -1/2 times 4 to the x, and y equals 2 times 4 to the x power. Okay? And we're going to graph those all in the same graph. So what I'd like you to do right now is pause this and go ahead and complete your table for y equals 4 to the x power. Again, remember what you need to do with negative exponents here and 0 exponents, and then complete your table for that one. So again, pause it, complete your table, and see how that looks. Alright, so for y equals 4 to the x power, alright, plugging in our -2, -1, 0, 1, and 2 for your exponents, we've got 1/16, 1/4, 1, 4, and 16. Okay, those are the 5 values that were into our table. And again, we're not always going to be able to graph all 5 of these values, but I at least want to see these 5 values appear in your tables when you're creating your graphs. Okay? So again, start maybe here, 0, 1. Alright, that's a nice easy point for us to graph. And then we can graph the next one here, which is 1, 4. That's another nice easy one to graph. And then our next one is 2, 16, which again, that's going to be all the way up here. So you can see that this line is really going to shoot up very quickly as my x values get bigger. Okay, now what about my other values? This is negative 1 comma 1/4. Okay, 1/4, that's less than a half. So I am drawing a point that is going to be really close to 0, but again, as we talked about, it's not actually equal to 0. Okay? My negative 2 has an output of 1/16, which is a number that's even closer to 0, but again, still not equal to 0. So just like in the previous problem, what you're going to notice is that as I draw this line, as my x values get smaller, it's going to approach 0, but it's never going to get to 0. So I'm going to show that in my graph of this one. Okay, that's the first half of it. And then from here, we said that it is going to increase very rapidly, just like that. And that's what the graph of y equals 4 to the x power looks like. Okay? Now again, what I'm going to ask you to do is pause this, plug in negative 2, negative 1, 0, 1, and 2 into this function, and determine what your outputs are. All right, now for this problem, remember, order of operations, you're going to have to do your exponent part first, and then take that answer and multiply it by negative 1/2. So when you take 4 to the negative second power, we already know that's going to be 1/16. When you multiply that by negative 1/2, you're actually going to end up with negative 1/32. 4 to the negative first power is going to be 1/4. Multiply that by negative 1/2, and you're going to get negative 1/8. 4 to the 0th power is 1 times negative 1/2 is negative 1/2. 4 to the first power is 4 times negative 1/2 is negative 2. And 4 squared, we said, was 16. Multiply that by negative 1/2, and you're going to get negative 8. Now, here's where this one's a little different. Okay? Notice that over here, all of your x values were positive. Sorry, all your y values. And over here, all of your y values are negative. Why? Because after we did our exponent problem, we went through and multiplied all the results by negative 1/2. So this is what this one's going to look like. Negative 2, negative 1/32. Again, that's going to be really, really close to 0, but it's now actually going to be on the bottom part of that. Negative 1 comma negative 1/8. Right into here. 0 comma negative 1/2. Could be here. 1 comma negative 2 is here. And we can actually graph my last point, which is 2 comma negative 8, which is going to be right here. So now, as I go to curve my graph here, okay, it's going to now look, as my x values get bigger, my y values are going to get a lot smaller because they're getting negative. And as my x values get smaller, just like before, it's going to get closer and closer to that 0 value. But instead of staying above it, now it's going to stay below it. All right. And again, the last thing I'd like you to do is go ahead and pause this, complete the table for the last one, and then we'll come back and we'll compare values to that. All right, so as we follow the order of operations in this problem, again, we've got to take 4 to the negative second, 4 to the negative first, 4, 0, 4 to the first, and 4 squared. After we do all of those, then you got to multiply everything by 2. So 4 to the negative second is 1/16. You multiply that by 2, and you're going to get 1/8. 4 to the negative first is 1/4. You multiply that by 2, and you're going to get 1/2. 4 to the 0th power is equal to 1. times 2 is going to be 2. 4 to the first power is 4 times 2 is 8. And 4 squared is 16 times 2 is going to give you 32. Okay, go ahead and plot those values. Again, I'm going to start at 0, 2, which is going to make it a little bit above my other one. Then I've got 1, 8. 2 comma 32, again, that's going to be way up here off the graph. Okay? Negative 1 comma negative 1/2 is going to be here. And negative 2 comma 1/8 is going to be a little bit below that. So as we go through, you're going to notice that my green line, my green graph, is going to be a little bit above my red one, because the values are a little bit bigger for each of those values. But again, as it starts to move on, it's going to get closer and closer to 0 as that moves on as well, as my x values get small. Okay? Again, we do have one that's a little abnormal compared to the other two. Why does this one go below it instead of above it? That's because of the a value here that was a negative value. Okay? When that a value is a positive value, as it is in the first and the third one, my graphs look more like this. When my a value is negative, my graphs are going to look more like this. That's something that you're going to want to think about tonight as you're doing your homework, because that's going to have an impact on how that graph should look like when you get done. Okay? So, once you are done with these notes, you're going to need to get a piece of graph paper, because a lot of today is graphing, okay? And complete the following homework assignment. It is going to be page 461, numbers 2, and then 4 through 14. So some of these are going to be creating an equation from a table, and then some of them are going to be graphing. Again, when you go to graph, I expect a table of values that has at least 5 values in it. Okay, that doesn't mean that all 5 values are going to be able to show up on your graph, but it does mean that I expect to see 5 values in your table.